This $30 PVC frame pulls drinkable water straight out of the air. No well, no pump, no electricity, no plumbing connection of any kind. In Morocco right now, a system built on exactly this principle is producing thousands of liters a day on a mountainside, supplying entire villages that previously had no reliable water at all. That part is completely true, and I am going to show you the physics, the yields, and the full build. But I am also going to give you one number in the first 3 minutes that decides whether this works on your land or produces absolutely nothing. And almost no video on this subject will show it to you. By the end of this, you will know exactly how much water a square meter of mesh produces. The 4 separate places where this is running today, the complete parts list with prices, the single site condition that determines success or failure, and what you must do before drinking a drop of it. Let me start with the distinction that the entire subject rests on, because getting this wrong is why most people build one of these and collect nothing. There are 2 completely different ways to take water out of the air, and they are separated by an enormous amount of energy. The first is condensation, which means taking invisible water vapor and cooling it until it turns into liquid. That process has a hard physical cost. Turning water vapor into liquid water requires removing roughly 2,260 kilojoules of heat per kilogram, which works out to somewhere around 0.6 of a kilowatt-hour of energy for every single liter you produce. And that is the theoretical floor before any real machine's inefficiency. This is precisely why commercial atmospheric water generators, the machines you see advertised that plug into a wall and make water from air, consume so much electricity. They are running a refrigeration cycle, and physics sets the bill. The second method is interception, and this is the one that costs nothing. Fog is not vapor. Fog is already liquid water, suspended in the air as droplets between roughly 1 and 40 microns across, small enough to float and drift on the wind. Those droplets are already condensed. Nature did the expensive part for you. All you have to do is put something in their path that they will collide with and stick to, and then let gravity take them down into a container. That single distinction is the whole technology, and it explains everything about where this works and where it does not. Now, there is a middle option between those 2, and it deserves a mention because people constantly confuse it with fog collection. Dew harvesting works by letting a surface radiate its heat away to the night sky, which cools it below the surrounding air temperature, at which point water vapor condenses directly onto it. That is genuine condensation, and it happens without any machinery at all, using the night sky itself as the heat sink. Special radiative surfaces and foils have been developed specifically to maximize the effect, and there is an international research body dedicated to it. The catch is the yield. Dew condensers typically produce somewhere in the region of 1/10 to half a liter per square meter per night, which is roughly 10 to 50 times less than a good fog collector produces in a day. There is also a long history of ambitious dew structures that did not work. In the early 20th century, a Russian engineer studied ancient stone mounds in Crimea and built a large condenser based on them. A French engineer later built an enormous concrete air well in Provence in 1930, designed to condense water from the air on a large scale. Both produced dramatically less water than intended, and the Provence structure is remembered mainly as a beautiful failure. The lesson from those attempts is the one running through this entire video. If you must pay the energy cost of condensation, the water becomes expensive. If nature has already paid it and handed you fog, the water is nearly free. You are not manufacturing water, you are catching water that is already there, already liquid, already floating past your property and currently drifting on to somewhere else. Now, let me show you what that catch is worth in liters. A well-sited fog collector typically produces between 2 and 10 liters per square meter of mesh per day. Some exceptional sites do far better during peak fog season, and marginal sites do considerably worse. Take the middle of that range, at around 5 liters per square meter per day. A small home-built collector of 2 square meters, which is a frame about the size of a large door, produces roughly 10 liters a day on a good fog site. 10 liters is drinking water for 2 or 3 people every day from $30 of PVC and mesh, with no moving parts and nothing to plug in. Scale that up, and the numbers become serious. 40 square meters of mesh, which is a single large commercial collector, produces on the order of 200 liters a day. Now hold that against what water actually costs when you do not have it. Drilling a residential well in the United States commonly runs between $5,000 and $15,000, and considerably more for deep or difficult ground, with no guarantee of finding usable water. Bottled water at typical retail prices costs more per liter than gasoline. And in the places where this technology is genuinely deployed, the alternative is not a shop at all. It is a woman walking several hours a day carrying containers, which is the reality for millions of households worldwide. That detail is worth staying with for a moment, since it explains why this technology exists at all and why it looks the way it does. Where water must be fetched, the fetching is almost always done by women and girls, and the hours it consumes come directly out of schooling and paid work. So a fog collector in that context is not primarily a water device. It is a time device, and the villages that install them describe the change in terms of hours returned rather than liters gained, which is also why the engineering is so deliberately simple. These systems are built to be repaired by the people using them, with materials available locally. Because a device that requires a specialist visit is a device that stops working the first time it breaks. Every design choice in this video follows from that constraint, and it is the reason a technology developed for the driest places on Earth is so easy for anyone to copy. Which brings me to the proof, and I want to show it to you at 4 separate scales. Start with the largest, in Morocco. On Mount Bout Mesguida in the At Bahrain region, south of Agadir, an organization called Darcy MAD operates one of the largest fog harvesting systems on Earth. The mountain sits in a position where thick fog rolls in off the Atlantic for a substantial part of the year. The project installed large fog collectors across the slope, piped the harvested water down to storage tanks, and connected it to villages that had never had running water. The system has been supplying those communities since 2015. It produces thousands of liters a day at peak, and it changed daily life in a specific and measurable way. Since the households it serves were previously dependent on women and girls walking for hours to fetch water by hand, that project has won international recognition, and it is the strongest single answer to anyone who tells you this is a hobby project. Now, the scientific origin in Chile, the Atacama Desert is one of the driest places on Earth, with regions that go years between measurable rainfall. And yet, a dense coastal fog rolls in off the Pacific, which Chileans call the Camancaca. Researchers realized that this fog carried enormous quantities of liquid water past the coastal hills every single day. In the early 1990s, a project at the fishing village of Changungo installed around 90 large fog collectors on the ridge above the town. At its peak, the system produced on the order of 15,000 liters a day, supplying a village of a few hundred people who had previously relied on water trucked in. The project eventually declined for reasons that had nothing to do with the technology, involving maintenance, funding, and local politics, which is a pattern worth remembering. Chilean universities continue to run fog research stations in the Atacama today, and the scientific groundwork for essentially every fog collector on Earth traces back to that coast. Now, urban scale in Peru, Lima is one of the largest desert cities in the world, sitting in a region with almost no rainfall, and large parts of its population live in settlements on the hills above the city. With no piped water, those hills sit inside a persistent coastal fog. Communities have installed atrapanubelas, meaning fog catchers, on the slopes above their homes, harvesting water for household use and for irrigating small plantings. This is not a research installation. It is people in an informal settlement solving their own water problem with mesh and frames, and it works. And now, the historical scale, which is the most surprising of all, long before anyone published a paper on this, people understood that certain places produced water from the air. Ancient sites around the Mediterranean and the Middle East include structures that appear designed to encourage condensation and collect it. And there are long-standing accounts of communities in fog belts using trees, walls, and stone piles to gather drip water. The connection to trees is genuine and worth understanding, since a forest in a fog belt does exactly what your mesh does. The needles and leaves intercept fog droplets, which coalesce and drip to the ground. And in some coastal forests, that fog drip contributes a substantial share of the total water reaching the soil, which means fog harvesting is not an invention at all. It is a copy of what a coastal forest has been doing for as long as there have been coastal forests, and every collector you will ever see is an attempt to build a cheaper tree. There is one story from that tradition worth telling properly. On the island of El Hierro, in the Canaries, there are long-standing accounts of a tree that supplied water to the inhabitants and their livestock. The island had almost no springs, and the tree stood in a position where a trade wind cloud passed constantly through its canopy. Fog droplets collected on the leaves coalesced and dripped steadily into cisterns dug beneath it. The islanders did not think of it as a curiosity, since it was their water supply, and the tree appears on the island's coat of arms to this day. That is not folklore dressed up as engineering. It is precisely the mechanism I have just described, operating on a canopy instead of a mesh, and it is the reason several modern projects have paired fog collectors with tree planting. The logic is elegant. You install mesh collectors first, use the harvested water to irrigate seedlings, and once those trees establish and grow a canopy, the forest begins harvesting its own fog, and the mesh becomes unnecessary. You are effectively using temporary plastic to bootstrap a permanent biological version of the same machine. And projects along the Peruvian and Chilean coasts have done exactly this. So why does almost nobody in the developed world know this exists? The answer is not suppression, and it is not a conspiracy. It is far simpler and slightly deflating. Fog harvesting is deployed where it is desperately needed and nowhere else. If you live somewhere with reliable piped water at a fraction of a cent per liter, there is no commercial reason for anyone to sell you a fog collector, and no manufacturer builds a consumer product for a market that does not want one. The research funding, the NGO deployment, and the engineering attention have all gone to arid regions, with fog and no infrastructure, which is exactly the right allocation of effort and also the reason it never appeared in your hardware store. There is a second factor. This technology is geographically brutal. It works spectacularly in specific places and produces nothing at all 100 miles inland, which makes it impossible to market as a general product and easy to dismiss as a curiosity. If you happen to live somewhere, it does not apply. If you want the full worked site assessment method, the yield calculations, and the material specifications for your own build, everything is linked below. All the numbers shown rather than asserted. Now here is the catch I promised you, and it is the single most important part of this video. This harvests fog. It does not harvest dry air. If your location does not have regular fog, low cloud, or heavy mist, this device will produce essentially nothing, and no amount of clever construction will change that. So, before you spend $1, you need to answer one question honestly. Does fog physically move across your land, and how often? The good sites share a recognizable pattern. Coastal areas with cold ocean currents produce persistent advection fog, which is why the Chilean, Peruvian, Moroccan, and Californian coasts are the classic locations. Mountain ridges that intercept moving cloud work extremely well, since you are effectively standing inside a cloud. Elevated ground with steady wind is ideal, since the wind is what drives droplets through your mesh. The poor sites are equally recognizable. Dry inland areas with clear skies produce nothing. Sheltered valleys with no wind produce very little, even when fog forms, since the droplets need to be pushed through the mesh rather than drifting past it. And anywhere that fog appears, a handful of mornings a year is not worth building for. Here is how researchers actually assess a site, and you can copy the method exactly. They build what is called a standard fog collector, which is a 1 square meter frame of mesh mounted on a simple stand, with a gutter and a measuring container beneath it. They leave it in place for a full year, and they measure what it yields month by month. That single square meter tells them precisely what a large installation would produce on that spot, since the yield scales with area would strongly encourage you to do the same thing. Build 1 square meter first for around $30, and measure it for a season before you build anything larger. That is not caution for its own sake. It is the difference between a system that supplies your household and a rectangle of shade cloth rotting in a field. Keep a proper record while you do it, because the pattern matters more than the total. Note the date, the volume collected, and roughly what the weather did, and after a few months, you will see the shape of your site clearly. What you are looking for is not a single good week. You are looking for how many days per month produce meaningful water and whether the season is 2 months long or 8. You will almost certainly find that yield is wildly uneven, since fog collection is not a steady trickle but a series of events. A collector can sit dry for a week and then deliver its monthly total across 2 foggy nights. That unevenness is exactly why storage capacity matters as much as mesh area. Since a collector that produces 40 liters in one night and nothing for 5 days is useless with a 10-liter container, size your tank for the biggest event you record, not for the daily average, and you will capture everything your site actually offers. Now let me show you how to build it. The frame is PVC pipe, an 1.5 or 2 inch schedule. 40 works well. A 1 to 2 square meter frame takes $15 to $30 of pipe and fittings from any hardware store. Build a simple rectangle, glue the corners, and brace it. Since this frame will act as a sail in exactly the wind conditions that make it productive, the mesh is the heart of the device, and the material matters enormously. The standard is Rachel mesh, which is a knitted polypropylene shade netting, typically used at around a 35% shade coefficient. It is cheap, it is widely available as agricultural shade cloth, and it has been the workhorse material of fog collection for decades. Expect $10 to $30 for enough to cover a small frame. The physics of why that specific mesh works is genuinely interesting. If the weave is too tight, air flows around the collector instead of through it, and the droplets go with it. If the weave is too open, droplets pass straight through without touching a fiber. The correct mesh is a compromise that lets air through while presenting enough surface for droplets to strike. And researchers at MIT demonstrated that optimizing fiber diameter, spacing, and surface coating can improve collection efficiency dramatically over standard mesh. Doubling the mesh, meaning 2 layers with a small gap, generally improves yield and is worth doing. A word on material choice, since this is where cheap builds quietly fail. Buy shade cloth rated for ultraviolet exposure, because ordinary netting degrades in sunlight and begins shedding fibers within a season or two, which shortens the life of the collector and puts plastic into your water. Avoid metal mesh unless it is stainless. Since ordinary steel rusts continuously in exactly the permanently damp conditions this device creates, and the rust ends up in your tank. And avoid anything with a coating you cannot identify, particularly second-hand industrial netting, since whatever is on that surface will be washed into your storage by the first fog event. Food safe, ultraviolet stable, and knitted rather than woven is the specification. And it costs a few dollars more than the wrong material. The gutter runs along the bottom edge and catches everything that runs down. A length of standard vinyl rain gutter costs $10 to $20, and half a length of PVC pipe split lengthwise works just as well. Tilt it slightly so water runs to one end, and fit a downpipe into your container. The storage container should be food grade and opaque, since sunlight in a clear container grows algae within days. A food grade drum runs $15 to $40 used, and it should be closed apart from a screened inlet, both to keep debris out and to stop mosquitoes breeding in it. Add rope, ground anchors or stakes, and zip ties or lacing cord for another $10 to $15. For orientation, face the mesh directly into the prevailing fog-bearing wind, which on a coast usually means facing the sea. Height helps, since fog is often denser, a few meters up, and anything that blocks your wind will cost you yield. Total cost for a well-built 1 to 2 square meter collector lands between $30 and $80, and the commercial engineering exists as a reference point. The Cloudfisher, designed by Peter Trautwein with the German Water Foundation, is a 3-dimensional mesh system specifically engineered to survive the high winds that destroy flat panels, and it is worth looking at if you intend to build anything permanent. Now, the safety section, and this one genuinely matters. Water that has fallen through the atmosphere and across a plastic mesh is not automatically drinking water. The mesh collects everything the air carries, meaning dust, airborne pollutants, industrial particulates near urban or agricultural areas, and anything a passing bird contributes. The fog itself is generally clean, since it condensed from vapor, and the contamination happens at the mesh and in the gutter. So treat it as a raw source. Fit a first flush diverter that discards the initial run of each fog event, which carries the accumulated dust off the mesh. Filter it through sediment and carbon stages, and disinfect it before drinking, whether by boiling, ultraviolet treatment, or an appropriate chemical method. Clean the mesh and the gutter regularly, since biofilm builds up quickly on constantly damp surfaces. Keep the storage tank closed and screened, both for water quality and because standing water is a mosquito nursery. And check your local water rights. since a small number of jurisdictions have historically regulated rainwater and atmospheric water collection, and it costs nothing to confirm before you build. Now, the honest limitations, all of them. The first is that this is entirely seasonal in most locations, so your production follows the fog season and may stop completely for months. The second is wind damage. The conditions that produce good yields also destroy poorly built frames, and a flat mesh panel is a sail, which is precisely why the cloudfisher exists. Build for the worst gust your site sees rather than the average breeze, and expect that number to be considerably higher on an exposed ridge than in your garden. Brace the frame diagonally, guy it with rope to ground anchors on both sides, and leave the mesh with a little slack rather than drum tight, since a taut panel transfers every gust straight into the joints. A collector that survives 5 winters is worth far more than a slightly larger one that folds in the first storm. The third is maintenance, since mesh degrades under ultraviolet light over several years. Gutters clog and biofilm accumulates. The fourth is the water quality issue, which means this is never a drop-in replacement for a tested municipal supply. The fifth is that it is not scalable in the way people hope, since doubling your water means doubling your mesh area, and there is no clever trick that changes the yield per square meter at a given site. And the sixth is the one I keep returning to, which is that the site decides everything. A perfect collector in the wrong place produces nothing, and a crude collector in the right place produces water every day for years. So here is the honest verdict. If you live in a coastal fog belt, on a ridge that catches cloud, or anywhere that produces regular heavy mist, this is one of the highest value things you can build for $30, and it will keep producing for as long as you maintain it. If you live somewhere dry and clear, this is a fascinating piece of engineering that will not work on your land, and I would rather tell you that now than after you have built it. And if your site turns out to be marginal, meaning it produces water but not enough to drink from, do not throw the project away. Since there are uses that do not require volume or treatment, irrigation is the obvious one. 10 liters a day delivered slowly to the base of fruit trees or a raised bed is genuinely useful, and it needs no filtration or disinfection whatsoever. Livestock and poultry water is another, subject to basic cleanliness rather than drinking water standards. Greenhouse and nursery watering suits this perfectly, since fog water is naturally soft and free of the dissolved minerals that build up in soil from hard tap water. And washing water, for tools, hands, and general outdoor use, absorbs whatever your collector produces without any treatment beyond keeping the tank clean. So the yield threshold for the project being worthwhile is far lower than people assume, since only the drinking application demands both volume and treatment. Here is a claim worth checking, and I would like you to check it. Look up the fog harvesting project on Mount Boutmezguida in Morocco, run by Dar Sayhamdan, and read what it produces and who it supplies. Then look up the Chungungo project in Chile from the early 1990s and what happened to it afterwards. The first tells you the technology works. The second tells you that a working technology still fails when the maintenance and the funding stop, which is the more useful lesson of the two. So here is my question. If you had $30 in one weekend, would you build a single square meter of mesh and measure what your air actually gives you? Or would you assume your location is wrong and never find out? Drop your answer in the comments and tell me how often fog rolls across where you live, because that one detail decides everything, and most people have never thought to notice it. I read every one. Next time, I am going to show you the buried pipe that cools an entire house through summer using nothing but the temperature of the ground beneath it, with no refrigerant, no compressor, and no electricity beyond a single small fan. Subscribe so you do not miss it. And remember that the best technologies are usually the ones nobody can sell you, because they only work in the places that genuinely need them.